So now we're going to look at a very, very interesting part or an implication of projectiles. We'll begin with a problem. Yeah, it's called the hunter-monkey problem. Now what is this? It's a very popular problem. You might know about this. Let me set up the problem for you. So yes, a hunter is aiming his rifle right at the monkey, right? So his rifle is pointing. If you draw a line from the rifle to the monkey's head, it's a straight line. So he's aiming right for him. In other words, if the gun had a laser on it, the laser would be pointing right at the monkey's head. Now you are the monkey. And now you're able to see this. You're able to see the laser on your face somewhere and you're going, oh my God. You know your death is near. You look down and you see that it's not too high. You can jump and you can let go and land a little safely. Now you're thinking, you see that he's almost about to press his trigger. So you know by the time you jump, he would have pressed his trigger. So him pressing the trigger and your jump will be simultaneous. So what do you decide? Do you decide to stay or do you decide to let go and fall? That is the question. You know it's coming right at you. Should you stay or let go? What will your answer be? Think about it for a moment. Yeah? Now let's proceed. So now, the answer to this question might depend upon how far away you are, how high you are, many other things that the question does not have enough information. That could have been an answer. You cannot say the answer to that question without also knowing, say, what distance this is. So let's fix that distance. It's 20 meters. Yeah? What velocity? That might also be important. Yeah, because bullets just race away, right? Yeah. A velocity of 20 meter per, we'll make it 20 root 2 for obvious reasons per second. Let's say that is the velocity. And let the angle of this launch be 45 degrees. Yeah. So you might have had three answers. You would have said, I'll always stay. I'll hold on and stay. You might have said, I will let go, obviously. Or third, you might have said, it depends. Depends on what? Let's see which of these answers is correct. So the problem basically breaks down to having something shot at you with a velocity 20 root 2 at an angle 45. You're 20 meters away at a height of... Why didn't we give the height in the previous question? Because the information was enough to figure out what that height is. Yeah, because it's 45 degrees and you know the gun points right at the monkey's head. Yeah. So how high will the monkey be? That also has to be 20 because his angle is 45 degrees. So that is fixed. Then you know that the monkey is going to end up falling down in this line, correct? So if the monkey gets hit, it'll get hit only along this line somewhere. In other words, when the bullet's x coordinate will be what? Exactly, 20. Yeah, 20 meters. So when the bullet's x is 20 only, the collision can happen 100%, if at all it happens. Correct. So let's find out how long that will take. What's step number one? As always, resolve the velocities into two. In this case, it will be 20 and 20. And this will go away. Great. Now, looks pretty easy. Your velocity is 20 meters per second. You're going to take 20, you have to cover 20 meters. What time will it take? Yes. Yeah, so the time will be 1 second. So the bullet will take 1 second to reach this line somewhere. We don't know at what height the bullet will be. Yeah, not too sure. But then, if at all the monkey does die, it still has 1 second to live. Yeah, so it's a happy monkey. Not really, right? It has only 1 second. So let's see what height the bullet will be when after time 1 second. Yeah. The idea here is a bullet is not beyond the laws of physics and gravity, right? The bullet, even though in usual, it looks like it'll just cover a straight line. Truth is the bullet also will end up curving a little bit because of gravity. So the bullet's path is going to be something like this. It's also going to be a projectile. So you have to find out how far the bullet would have fallen. Because we think that the monkey would have fallen more. No. Yeah, monkey is much heavier, monkey will fall. Yeah. Of course, you're understanding that we're neglecting air resistance here, aren't we? You're assuming we're neglecting air resistance. So now let's answer this question. What height will the bullet be at? Why? What will you do for this? You have the time. All you'll do is write the equation, get the answer. So initial vertical velocity is 20 minus 5t squared. Yeah, 20 minus half g t squared. I'm writing this really fast because g is 10 and half of g is 5. So that equals what is your question? You have your time with you, it's 1 second. So 20 minus 5 is 15 meters because your t is 1. So this height you know is 15 meters. Oh wow. That must be a little surprising to you because the bullet actually ends up dropping a height of 5 meters, right? Yeah. Now what's there that's left to do? When will the bullet hit the monkey? When both of them are the same position. So if the monkey is either above this or below this, it escapes. Yeah, neglect for now, it will hit the body and all that. Okay, let's imagine the monkey is really small, only the head will hit. So everything else is neglected, so it has to be exactly at this point, 15 meters, only then it will hit. Let's see how likely that is. What is the monkey's motion here? The moment the bullet was launched, for the same time t equals 1 second, the monkey is also falling down. So the monkey's fall time, t equals 1 second for the monkey. Its initial velocity is, it's just letting go, it's 0. And what should we find? The s, right? The acceleration you know. So what will your answer be? You'll get half into g is minus 10 into t squared, which is 1 squared. So you get minus 5 meters as your displacement. What does that imply for you? It's 5 meters downwards. So the monkey starts here from a height of 20 meters and drops a height of 5 meters. Oh my God. The monkey ends up getting hit by the bullet exactly. Is that surprising you? Yeah, a tragic end of the monkey, right? So the monkey had 1 second to live and then it died. But if the monkey had stayed, what would have happened? Yeah, the bullet would have gone below it and it would have survived. So in this case, the answer surprisingly is just to say stay because the bullet's aimed right at you, but the bullet will fall. But by letting go, you're also falling. You're ending up hitting the bullet. Now you might ask, for this case, it's a coincidence. For most cases, letting go might be better. You've arranged the numbers very, very intelligently and somehow made it so that the bullet will correctly hit the monkey. It looks like a bad coincidence to me. I will not believe you. I like what you say. It could be a bad coincidence, right? Who knows? 20 I've fixed here, 20 I've fixed here, 45, all this. So what if it's a special case here? To answer this question, let's take a very different approach. Let's imagine we look at the same thing from the monkey's point of view. What will the monkey see? The moment the monkey is let go and the bullet has also been fired, both of them have various things that are different, right? But one thing is common between the two of them. And what is that? The acceleration g downwards. Both of them are falling at an acceleration g downwards. And in free fall, I told you that if you walk off a building and if you're jumping along and you have a friend with you and both of you are falling, as far as you look at each other, it's as good as neither of you is falling. The only way you know is by how, maybe by the air rushes at you or everything else is going upwards and you're feeling all confused. But neglecting air, and if you're looking only at each other, what will you see? A normal conversation. Both of you seemingly at rest. That's pretty much what's going to happen to the monkey here. The monkey's world, in the monkey's frame of reference, in other words, gravity can be switched off. Because in the monkey's world, it's at rest. So you apply its acceleration to itself, which means to every other body you will do that. So you do that to the bullet as well. You'll do that to the earth as well. So the monkey will see the earth coming up towards it at g. Yeah, but that's not too relevant for us right now. We'll forget it. So what does it mean? The monkey sees no acceleration for itself or for the bullet because their relative acceleration is 0. The crux here is that their relative acceleration is 0 because both of them are accelerating downwards. Then, what do you observe? What will the monkey see? The monkey will just see this velocity being the 20√2. The monkey will see it coming right at it and hit. Yeah? In a gravityless world, if the same thing had happened in space, what would you have expected? That's exactly what will happen now. In space, what will happen? If somebody aims at you and shoots, if it's aimed exactly at you as a straight line, then it'll come and hit you because there's no gravity. And in this world now, there is no gravity, right? We've added everything, we've taken away the G's. There's nothing else over there. So the bullet will take a straight line path and come and hit the monkey. That's what the monkey will see. Which means, here we haven't used anything. This velocity here is not even required. What have you shown? No matter what, if both of them let go at the same time, if the bullet is aimed right at it, the bullet will hit. Yes? Now, let's see if our calculations match through another method. So this velocity is 20 root 2. You know that this distance is 20, this was 20, so this must have been 20 root 2 meters, right? So your time taken, right, doesn't change in these two frames. Time is still 1 second. And this cannot change, right? What point of view you see the problem from cannot change the amount of time the monkey has left to live. In the previous case, the monkey left, and in our frame of reference, the monkey took 1 second. In 1 second, the monkey was hit. Here also it has to take 1 second. The interval cannot change. The time interval. So this is interesting. We can make it look even more difficult by asking the question, if the same thing had happened in the falling elevator, what would have happened? Yeah? That's pretty much a space. Space or a falling elevator are similar frames, right? Because inside the falling elevator, gravity is switched off. So it's as good as. Why is gravity switched off? You're falling, bullet is falling, elevator is falling, everybody is falling. As far as you're concerned, nobody's falling. Except that you'll hit after some time. But till then, for a while you can feel, hey, I'm flying inside the elevator. Yes? So inside the elevator as well, the monkey will just see the bullet coming right at it and hitting it. So that's a pretty counterintuitive result for most of us, right? Because most people think that we should just let go because the bullet would pass above. That comes from the intuition that bullets almost travel in a straight line. Now you know that letting go is actually more dangerous than staying. If you stay, you might still get killed because the bullet won't, diverge too much from its distance. So instead of hitting maybe in the head, it'll hit you somewhere in the chest or something like that. But if you do let go, you will surely get hit. Yeah? So we've shown these two here. So staying, maybe bullet will hit. Letting go, bullet will surely hit. Neglecting, air resistance. One small caveat is there. What is that? We said if it is pointed at you, it will surely hit you, following one small condition. I'm pretty sure some of you thought about this. And that is that the bullet's range must be at least equal to the horizontal displacement, 20 meters. So the monkey is here, right? The bullet's range must at least be this much, because otherwise it doesn't matter whether the monkey lets go or stays, because the bullet doesn't even reach that horizontal line. To hit, it has to reach somewhere on this horizontal line. If it never happens, it will never hit. So if you had also asked about a condition, when what the minimum velocity of the bullet must be for this to happen, you can calculate that by calculating the range to be equal to 20. In this case, depending on the question, this number will change. And then backtracking to, you'll know the angle, it's 45. Yeah? To get maximum range, you have to shoot at 45. Because that, you will finally end up hitting the monkey at the same flat line, right? That's when your velocity will be minimum. So you fix the angle as 45, fix the distance, and you can find the velocity that you need, that you need. Do observe though that the slower and slower your velocity becomes, the longer and longer the monkey has to live. Because if you hit at infinite velocity, the monkey will get hit almost there. Which is pretty much what bullets are. Bullets are very, very fast, so we always imagine that to happen. But the slower and slower your bullet, the longer and longer the monkey has to live. At your minimum velocity, the monkey will land and you will hit at the same time. But any lower than that minimum velocity, the bullet won't even reach that final point. So yes, not always will the monkey die. There is some hope in the world. If the velocity is enough to cross this line, then if the monkey lets go, it's doomed. Now using this idea, the idea of the hunter-monkey problem is to hit at relative accelerations. When two bodies are falling, taking the frame of the falling body can actually simplify the problem. Let's solve another problem to understand this. Let's set up the problem now. So yes, you've seen these, if you play Angry Birds, you've seen one blue angry bird that breaks into three, right? Let's look at that now, and let's impose one more constraint on it. Let us say the three breakings, right? The three little birds end up having velocities lined up like this, right? Now what will that imply? That will imply that their horizontal components are the same. The ux for all is a constant. That's our constraint. Now we are asking, as the three birds are flying, if one of them, if the bottommost one looks up and sees the topmost one, what kind of motion will it see? Now the answer to this question that I got in my classroom was it will not see the topmost one, because the second bird in the middle will block it. So yes, I agree. So if it looks up at the second one, the middle one, what will it see? What kind of motion will it see? I'll give you some options. Will it see the motion being a projectile? Is that possible? So something like this. Yeah, let's move to a different page. So we'll have all our 4 options. Yeah, one is a motion like this. One is where it goes up and comes down. So the bottom bird will look at the top bird going up and coming down. Yeah, but nothing else. Third option being, it'll see the bottom bird going up with an acceleration. And fourth one being, it'll see it going up with a constant velocity. So here clearly there is an acceleration, here clearly there is an acceleration, right? It's going up and coming down. So these are our 4 options. What is your answer? Now think about that answer, pause for a moment, and then come back. We'll understand how to solve this problem. Now the intuition for this problem is if the bottom bird sees the top bird, it'll look like some kind of a parabola. Yeah. So it's difficult to visualize, which is why sometimes mathematics might help us. Let's look at what we have to do, right? Solving problems in relative is very, very easy. What is the bottom bird's velocity in the horizontal? Some ux. Yeah, we'll call it ux1 because it's the first bird. It'll have some vertical velocity uy1, correct? Because it ended up having some velocity like this. Now bird 2, we'll use a different color now, let's say had a velocity like this, only then it'll end up above, right? But what was common? The ux. ux2 is also same number, but uy2 will be a different number. Otherwise, both if ux and ui are same, both the birds will be sticking to each other and flying. Correct? It's not happening. So ui has gone above. That's why the bird has gone above. So you will have, and after some time, the bird will be somewhere over here. So you know now, by now I'm pretty sure that throughout the motion, both these birds will be along the same vertical line. Which is another way of saying they'll not see each other moving horizontally. So the bottom bird won't see the top bird moving this way or that way, right or left. Yes, that's 100% fixed. But let's not do that in any intuitive way. Let's just do it mathematically so that we know we are sure. So we first have to calculate our velocities. What about a relative velocity? Relative velocity. In other words, the velocity of 2 in one's point of view. What's that going to be? We'll first do it in the x direction. It's going to be ux2 minus ux1. Same old 1D motion, relative motion, okay? None of the formulas change, none of the formulae change. So we have velocity of 2 in the frame of reference of 1 in the x direction to be this you know is 0. Great. What about velocity of 2 with respect to 1 in the y frame? Because that's what you do, right? How cares whether the body is going like this, flying is happening? None of that. You can break it down into 2 motions. So you do that now, you will get uy2 minus ux1. Sorry, uy1, right? That will be equal to some number. We know that this will be equal to this arrow. Yeah? Let's call this delta vy. I'm just using some names to make our representation easier. None of this is that important. Right? The names that we use. Delta vy is some number, but it's a constant. This doesn't change. Do you realize that? Because uy1 is a constant, uy2 is a constant, so delta vy is a constant. It's the difference between the two. Done. What about the acceleration in the x direction? Acceleration 2y in the x direction. Both of them have 0 acceleration, so 0 minus 0 equals 0. Along the x, does either of the bird have an acceleration? No. Only g acting downwards. So in our y direction, maybe there we have a difference. But do we? Both have an acceleration g, which is what our hunter monkey problem set up to, right? It was a setup to understand this even better. So the relative acceleration in both directions is 0, which means none of these can be correct. This can't be correct, this can't be correct, this can't be correct. When I say none of these, A, B or C can't be correct. We already arrived at our answer, but let's acknowledge what's the beauty over here. Because when I think about this problem, right, the bottom bird is going, the top bird is going up. It's always in the straight line. But we think when we start to fall down, I'll see the top bird falling down also. So people tend to say, choose this answer in one sense, where they'll say it look like the top bird is going up for a while and then down for a while. Because they imagine when the bottom bird is coming down, the top bird is also coming down, no? So it's kind of not being able to go completely into the bottom bird's frame, which is why math is there to help us. So this is the bottom bird's world. These 4 numbers are enough. Yeah? Velocity is being 0 horizontally, vertically there's some velocity, acceleration in all directions 0. What kind of motion is this? Body 2's motion from body 1's motion. Yeah, bird 1's motion is just some delta Vy velocity upwards, no acceleration in any other direction, no velocity in any other direction. So what will it see? It will just see the top bird going up with a constant velocity. Now that might be counterintuitive for many of you. It was for me when I thought about it first. Wow. So the bottom bird sees the top bird, it will just see it going up with a constant velocity, even when both of them are falling down. Yeah. Of course, after the bottom bird hits, then things change because the relative acceleration won't be g anymore. Yeah. So this gives us a glimpse of how we can simplify problems by taking another frame of reference. You'll see that again in an inclined plane problem. But before that, one of the questions we can ask you now is what we did in 1D, right? We threw one ball up, one ball down and asked when will they collide. We can just make a 2D version of the problem. And I'm saying just because it's hardly any different. So I can give you a problem that a ball that's going like this, another ball that's going like that. Let's say they'll collide. They may or may not collide. Yeah. You might have to find out if they collide, how long they take. But again over here, the insight will be that the relative acceleration is equal to 0. So you'll enter the ball's frame, apply relative acceleration is 0, then calculate horizontally what must happen, vertically what must happen. Yeah. If they must collide, they can't be thrown like this, right? Where this velocity is larger. Then clearly they won't collide. Yeah. So you can think of some constraints here as well. Let's start thinking about it together. One of the constraints can be that, see, this velocity, right? Horizontal velocity and this. If they're pointing this way, then you're pretty sure their paths will cross. But then what must happen then? Their vertical velocities we have to check. Yeah. If, let's say this, no? If we have some vertical velocity like this, some vertical velocity like this, such that they are pointing, one will point here, one will point here. Can we say that they have to collide? Think about this question, no? If we have infinite depth. If we have infinite depth, will you agree that they have to collide? Think about the question. Why am I claiming this to be true? If this is true, if I can go to the frame of space, because I realize when the relative acceleration is 0, I can think of a space or a falling elevator, then this ball has to go here, this ball will go somewhere there. Yeah. Now, if these two velocities are matched, only then will the collision happen. So we aren't confirmed. Correct? Why? I could have a velocity like this passes the line like that, and then this can go like that. Even in space, it's possible. In space, it's possible that these two won't hit. If I shoot one like this, shoot one more like this, they might miss. Which means we cannot say in general that there will be a collision. So there have to be some conditions that are satisfied. But to satisfy those conditions, what I'm pointing out to you is you don't have to think of them as falling balls. You can think of them as straight balls flying in space. So let's just make up a problem. I shoot a ball like this, right? At some velocity. I shoot another ball at some velocity. What can you forget for now? That there is any acceleration, because relative acceleration is 0. So all you'll do is, let me call this u1, let me call this u2. I'm doing it variables so that we get a general idea. Yeah, I could make up some numbers here, but not required. So you'll have u1 cos theta 1 here, u2 cos theta 2 here, assuming these angles are theta 2 and theta 1. Yeah. So the vertical will be u1 sine theta 1, and here it will be u2 sine theta 2. So what we don't need is the central vector, yeah, because we've already broken it down, keeping it as only like a useless appendage that we are having. So we have this here. Now what should you calculate? How long will these two take to collide? That's a very, very easy thing to calculate. Yeah. Now once you calculate that, that'll just be this distance divided by u1 cos theta 1 plus u2 cos theta 2. Now I'm being a little imprecise here. If you represented these with the appropriate signs, then this would have actually pointed that way with a negative u2 cos theta. So it'll come down to this, but yeah, I'm assuming you know that. What I mean is this will still be v2 minus v1, the velocity with which they approach. But because you've written it in the left direction, they add up. The scalar quantities, the speeds add up. So you add this over here, this will be your time. What should you find out now? Now their times are equal. Yeah, so sometime they'll take to come and meet here. This time will not be different for both of them. Then what must be constant? So what must be constant? this must be equal to this, right? u1 sine theta 1. In other words, the vertical velocity of ball 1, this velocity, and the vertical velocity of ball 2 must be the same in this case because they're being launched from the same height. Yeah, just took a case like that. So the vertical velocities have to be equal if they're being launched from the same height. So you can think of other constraints as well, right? I can make another problem seemingly difficult by throwing two from different heights. Yeah, nothing different. Relative acceleration is 0. So your problem will break down to something being thrown like this, something either up or down or whatever is happening being thrown like that. All you have to do is calculate this way without any acceleration and calculate if the conditions are being met. If they are, then you can calculate the time. The time will be your answer. To cover this horizontal, you have to calculate the time and that will be your answer. Again over here, you can go to the adaptive and there are problems which test you on these, but we've given you every single thing you need to be able to solve those problems. Relative acceleration being 0, calculating the horizontal, calculating the vertical, checking if they meet what should happen. We've given you some condition for that. So you're good to go.